Welcome back to The Explainer. Today, we're diving into a massive piece of AI news. We are tackling the absolute mystery of why artificial intelligence models make the specific decisions they do. As AI systems get more and more complex, their internal logic is getting seriously obscured, and that's creating a major headache for data scientists and engineers who actually need to trust these systems out in the wild.
It really boils down to one ultimate question. Why did the AI make this decision? I mean, this is literally the question that keeps machine learning engineers awake at night when a model fails in production, right? Or when a regulatory audit suddenly demands to know exactly why a specific outcome happened. If you can't answer that question, well, you just can't fully trust the system.
And that directly brings us to the whole black box problem. Basically, it's a predictive model that spits out outputs without exposing the internal mechanisms or the logic behind its decisions. The sources make a really crucial point here. In critical contexts, predictive accuracy alone just isn't enough anymore. If the underlying reasoning is hidden, getting a high accuracy score on a test set doesn't guarantee your model won't just catastrophically fail when feature distributions inevitably shift in the real world.
So, here's our roadmap for today's explainer. We're going to break down the black box problem, introduce the IMEX solution, unpack the math, look at some benchmarks, dodge a pretty hilarious naming collision, and finally, talk about auditing your AI in production.
All right, let's jump right into the core issue, the exact failure point of current explainability tools.
So the reality is that current explainable AI, or XAI methods, have some pretty severe limitations. Traditional tools, things like in-base or additive methods, they mostly just guess. They approximate important scores rather than actually measuring them. They rely heavily on perturbation, which is essentially just tweaking inputs to guess what changes, or they use surrogate models, which just introduces a whole new set of error boundaries. But the biggest issue? They completely fail to capture complex, higher-order dependency chains. They basically flatten or just throw out those latent synergistic mechanisms entirely. They might tell you a specific feature is important, sure, but they totally miss the complex web of interactions actually driving the model's behavior.
Okay, so how do we fix this? Let's dive into the IMEX mapping solution. Enter IMEX. That stands for Interaction-Based Model Explanation. Now, this is a post hoc framework that completely shifts how we handle explainability. It moves it from a sketchy approximation task to a direct measurement problem. It essentially builds a literal interpretability map. And what makes IMEX a real game changer is that it doesn't impose cardinality limits. It evaluates feature subsets larger than just two, which exposes all those hidden latent mechanisms that your standard feature importance scores just flatten into nothing.
To really understand how it does this, we need to unpack its twin engines, PCS and PCI.
Let's de-jargon this a bit. Think of static correlation power, or PCS, as a feature's solo performance. It measures the standalone contribution of a single feature to your target prediction, operating totally independently. Then on the flip side, you've got interaction correlation power, or PCI. This is your team synergy. It captures the non-additive, complex effects that emerge when multiple features interact. Because, let's be real, in the real world, variables almost never contribute linearly. A model might only trigger when feature A and feature B cross very specific thresholds at the exact same time. PCI measures those exact interaction patterns directly.
By putting these two metrics together, engineers can literally reconstruct the model's actual decision topology. PCS quantifies the baseline feature weight, while PCI highlights those nonlinear interactions. And because it's looking at groups larger than just pairs, you get the whole picture. Why is this so absolutely crucial? Well, imagine a feature with a super low PCS. On its own, it looks completely useless, right? But it might actually be essential because its PCI contribution activates under very specific conditional states. Without PCI, you would toss that feature and completely break your model's edge cases.
But does it actually work in practice? Let's look at the empirical validation.
To prove the framework works, the researchers validated the PCS component against in-base, which is a state-of-the-art attribution method using XGBoost predictive models. And they ran this on synthetic data sets, specifically scenarios called purchase and store and gas station. Now you might be wondering, why synthetic data? It's absolutely vital here because it gives us a perfectly controlled environment. We explicitly know the true underlying dependencies and the structural rules governing the data. We know the ground truth.
Check out the stark contrast in these F1 scores. Remember, F1 measures the ability to correctly identify the truly relevant features. For the basic correlations in the purchase and stored data, InVase and IMEX are pretty neck and neck. But look at the gas station dataset, specifically predicting the number of pumps. InVase completely whiffs it, I mean, an F1 score of straight 0,0,0,0. It entirely misses the indirect conditional dependencies. Meanwhile, IMEX's PCS metric absolutely dominates with a 0.794. It successfully recovered the true underlying structure.
So why the massive gap on complex data? It mostly comes down to multicollinearity. Standard tools tend to arbitrarily split importance between correlated features, or they just assign near-zero scores to genuinely predictive variables. IMEX completely bypasses this variance splitting problem by isolating the actual predictive signal directly. It catches those weaker but highly meaningful signals that other tools are blind to. And as we just saw, it is wildly good at uncovering conditional if-then dependency rules.
Now, before we talk about deploying this, we need to take a quick detour to save you a massive debugging headache. There is a rather hilarious, but honestly pretty dangerous, naming collision happening right now. The AXI IMEX we've been talking about is an explainability framework. But NVIDIA also has a tool called IMEX. Except NVIDIA's is a Unix daemon-based service for GPU memory sharing on NVLink networks. And it requires root privileges. They share the exact same acronym but solve entirely different problems. So if you're trying to audit your model, please, for the love of all things holy, do not mistakenly install the NVIDIA IMEX systemd package, or you are going to have a very, very confusing afternoon.
All right, crisis averted. Let's pivot back to how you can actually audit your AI in production today.
Here's a highly actionable step-by-step deployment pipeline based on the framework. First, pin the exact RVI paper, that's 2607-14096, to pull the algorithmic pseudocode. Second, run PCI on your validation splits to map out your baseline importance scores. Third, and this is key, validate your PCI under distribution shifts so your interaction scores don't just randomly flip due to sampling noise. Fourth, bake this interpretability map into your monitoring stack to set up alerts for interaction drift. And finally, use both metrics to audit multicollinear features so you can confidently drop redundancies and actually improve your model's generalization.
I really want to highlight this specific quote from the source material because it kind of hits the nail on the head. The framework does not replace model training, it replaces post hoc approximation, keeping the explainability layer decoupled from the model architecture. This decoupling is the absolute secret weapon here. You compute these metrics after inference on the exact same inputs that generated their prediction. Because of that, you can completely swap out your model's entire backend without having to rebuild your audit pipeline from scratch.
So as we wrap up this explainer, I want to leave you with a thought to chew on regarding your own stacks. Are your current models hiding spurious dependencies in their interactions? Because if you are only relying on traditional feature importance scores, you are probably only seeing half the picture. It might just be time to map the truth. Thanks so much for joining me today, and keep questioning the black box.